part. You understand? The circuits in the diagram below now, you have series connection of different what? Resistors. This is R1, this is R2, and this is your R3. Now this junction we have what we call different potential differences. That's EMF. Now you have your E1, E2, like that. Now at this junction there are different 2 points. You have point B and point A. Now if you say a loop, what do you mean by a loop? It is defined as a close connecting path. You understand? The circle in diagram below has two junctions, A and B. Now point A, B, C are the junction of the what? Second diagram. Now, what are we trying to say? This is a loop. This is a complete loop. This loop too. You understand? A complete circuit. You understand? Which has nothing to what? Bisect in between. This could be a loop and this could be a loop. So there are two loops in this what? Circuit. Now let's proceed to Kirchhoff's current law. What does the law state? The algebraic sum of the current flowing into any junction N is 0. Do you understand? Now, the sum of the current flowing towards a junction N is equal to the sum of the current flowing out from a junction. Now, when I say a junction, this could be a junction. Some currents are actually coming in. Let's say this is I1. This is another I2. This is another I3. Are you getting it? Now, this is I4 and this is what? I5. Now you have to understand that this is the junction. This is the midpoint where what? Currents are either flowing in or flowing out. Now if you look at this current now, it's actually flowing into this junction. I12 is flowing into, I2 is flowing into, so we have I1, I2, I3. They are flowing in, whereby I5, I4 are flowing out. So the algebraic sum, you understand? Algebraic sum of the what? Total current flowing along this particular junction is the law. You understand? It was actually what Sir Kirchhoff was actually trying to talk about, that the algebraic sum of the total current flowing into a particular point must be 0. Meaning that the total current flowing in, you understand? The total current, you just say summation I to 1. Do you understand? Summation I to 1 to, let's say, current. It will now give us something like summation I to 1 of n, or you say summation n to 1 equals your I to let's use I here, something like this. Summation n I to 1, then your I. You understand? So you get it. Now this one will be representing current into the what? The junction. So if we are to consider current into the junction, now we have your I1 plus your I2. Sorry. Yes, I2. I1 is flowing in, I2 is flowing in, then I3 is flowing in. So plus your I3 will now equal to those currents that are flowing out. That will be I4 plus your what? I5. So if you bring them in, you have your I1 plus I2 plus I3 minus I4 minus I5. You can see it becomes 0. So this is what Kirchhoff is actually trying to talk about. So the algebraic sum, when I say algebraic sum, this is what we call the algebraic sum. Why are these particular ones negative? They are negative because of their what? Direction. Their direction is what? Outward. Why these are positive? Because their direction is what? Coming in. So well, if you can establish all this, then you'll be able to what? Obtain your what? Your resultant of the algebraic sum of all the currents to be what? 0. That is a simple illustration of what? Kirchhoff's current law. That is the algebraic sum of the total current. I want to define it again. What is Kirchhoff's current law? It's defined that the algebraic sum of the current or the total current flowing into a particular junction must be 0. That's the law. So meaning that by the time you must construct such expression to actually make sure that the algebraic sum is what? 0. So that is as regards Kirchhoff's current law. Now let's go to Kirchhoff's voltage law. Now under the Kirchhoff's voltage law, what do you have? It says that the algebraic sum of the potential difference in any closed loop, including those associated with the EMFs and those of the resistance element, must also equal to what? 0. And for current, we are talking about a point. For voltage, we are talking about what? Remember, we already said what loops are. This is loop 1, this is loop 2. So if you have current here, probably resistance here, you understand? Now, we also have what we call, let's say V1 here, let's say R3 here, R4 here, I4, I3. You get? Now, the sum total of what? Of a voltage in a loop. The algebraic sum of the what? Look at the algebraic sum of the potential difference in any closed loop, including those associated with the EMFs and those in resistance element, must be equal to what? 0. Meaning that by the time you sum total, you have to sum the total of what? The current. Let's say you have here as one I1, then that's your potential difference, which is your VI, must be equal to 0. The algebraic sum of all the voltage in both loop 1 and loop 2. You know, mind you have to treat loop 1 separately. You understand? So it means that algebraic sum of I to 1 of what? First loop must be 0. The algebraic sum of what? I to 1 of what? Second loop must also be what? 0. So this is for second loop and this is for first loop. That is just the analogy or the analysis when it comes to Kirchhoff's voltage law. The total voltage in this loop must be what? 0. The algebraic sum of the voltage in this second loop must also be what? 0. In the exercises that follows, you can see we have different exercises there. Just sit down with them and you'll be able to what? Get those questions properly. Like the number 1 now, it's talking about conductivity. Let me do the analysis. For the exercises, we have number 1. What does number 1 say? Number 1 says that the length of that wire is 100 centimeter. Remember, 100 centimeter is equivalent to 100 exponential minus 2 meter, which is equivalent to what? 1 meter. We also have cross-sectional area. The cross-sectional area has been given. A cross-sectional area of, so we have your A as 2.0 exponential minus 3 meter per second. Meter seconds, right? Now, or meter square. Now, that your meter square is the actual SI unit of what? Area. You've gotten your cross-sectional area. Now, we now said with electric conductivity of 5.0 times 10 to the power 5. Now, you are given conductivity. You need to be very smart. You are given conductivity to be what? 5.0 exponential 5. With ohm meter raised to power minus 1. Mind you, ohm meter is the SI unit for what? Your resistivity. Hope you are getting that. There was an error the other time. Please, you have to flash back to the to where we spoke about resistivity and what? Conductivity. Where I said conductivity is the what? Inverse of what? Resistivity. Now resistitivity's SI unit is what? Ohm meter. While conductivity is your what? Siemens. Siemens per what? Per seconds. So those are the corrections there. So for the question 1 now, that's how you have to what? Break it down. So if you are given conductivity, just look for the inverse. For you to get your resistivity, inverse of conductivity gives you resistivity. So just look for the inverse of what? 5.0 times 1 over 5.0 times 10 to the power 5. You understand? So when you look for the inverse of this, you'll be able to obtain your what? Your resistivity. So it is with that. If you look at the question, it says calculate the resistance of the wire. Calculate the resistance of the wire. So we've gotten our length to be 1 meter. We've gotten our area to be 2.0 exponential minus 3 meters squared. Now we've gotten our resistivity now to be 1 over 5.0 exponential 5. Right? Now ohm meter, you understand? Ohm meter all raised to power minus 1. Now if we've gotten the resistivity to be this, because the area to be this, we definitely can obtain what? Our resistance. So that will give us what? Ohm equals AR all over L. So your R will now give you what? Over A, over lesson. So if you cross multiply and make your R square from that, it's going to be resistivity times length divided by A. So resistivity is what? Remember, we said it is 1 over 5.0 times 10 to the power what? 5 times your length, which is 1, all over your area, which is what? 2.0 times 10 to the power minus 3 in meter square. So if you can compute it with your calculator, you'll be able to obtain your resistance. So that is a breakdown of question 1. Question 2. A battery of EMF of 10 with an internal resistance of this connected to an external resistance of this. Calculate the PD across the cell. Write out your parameters first. The EMF of the battery is 10. Right? Now, we also have the internal resistance. That's a small r. The internal resistance is 2 ohms. We have the external resistance. We have the big R. The external resistance is 6 ohms. So you are told to calculate the potential difference across the cell. Now, if your E equals IR, remember this formula, I small r. So from there you have your E to be I into bracket. You understand? So from there you'll be able to obtain your current. From there you should be able to obtain your current. So it is the current and your resistance you use to obtain your potential difference. Now at this junction, now what do? Your E is 10. The current is what we are looking for. So add your 6 plus 2, you have your 8. So your current here is 10 divided by 8. That gives you 1 point. If you divide this, you have 1.25 amps. So that's the current. So if you want to obtain the potential difference, what do? You want to obtain